Okay, so we've been talking about the EEG data, and what I wanted to do is show you here a figure of where the channel layouts occur on this particular EEG. And I'm sorry, it is a little bit hard to read some of these numbers, but you remember I told you channels 61 through 64 were near the eyes. Then you can see like 1 and 2 and 3. Not finding 4, it's here somewhere. 4, 5, 6, 7, 8, 9, 10, 11. So the channels over here are on the right side of the head, or the left side of the head, and the channels here are on the right side of the head. So it's not like a radiographic image. The true left is truly left and right is truly right. It's not reversed. So you can see the channels at the back of the head are 36, 37, 38. Here's 33, 34, 36, 38. Sorry, this is 35, 37, 39. I'm not reading too well this small print. Anyway, this shows you the physical location of the 65 channels. CZ, your reference electrode, is right here at the top of the head. Let me show you a, show you a photo of the cap actually placed on a person. So here are those channels that are monitoring eye movements right here. And then this one is kind of at the bridge of the nose. The CZ is up here at the top of the head. These make contact with a saline soaked foam. So it's a little piece of foam inside of here. It is soaked and saturated with a saline solution. So it's a high impedance electrode contact. The cap is held in place with these little elastic things, and then each electrode has a cable coming out. What comes out that you don't see at the back of the head is a 64 wire cable. Here's another one. This is, I think, probably this is probably a 256 channel EEG. You can see it just has the layout at a different place. You have extra facial monitors. Here's a more conventional EEG cap, which is actually a true cap. Contact here is made with a conducting gel. It is a lower impedance contact than the one that we have in our lab, which is made with the saline solution, but often viewed as being a little more comfortable for the person who's having the EEG taken. So you're basically getting brainwave data from each of these electrode areas. So you can see that it's only mounted on the scalp. So if there is a source within the brain that is creating electrical activity, these are kind of like pickup microphones. Multiple electrodes will often pick up on the same source of activity. And the other thing to keep in mind is that they're picking up electrical activity of cells coming through hair, skin, bone, and lots of other tissue. So as a general rule, it is felt that the EEG does not really measure sources that are much below a half an inch to an inch or 1 to 2 centimeters below the surface of the scalp. Otherwise, the signal will tend to get lost, as well as act like more of an antenna. If it's deep within the brain, its signal would be spread over all the antennas or all of the probes and greatly attenuated. So let's look at your data that I've uploaded. This file called class data. You notice it is a 65 by 121 893,000 array. The 65 represents the number of channels. And so if we look, that in this data set is represented by rows. So you have 65 rows. So each channel is a row of data. The way the data set is set up currently is each column is a time point. So each column is just the array number. There are 121,893 columns. This data is sampled at 500 samples per second. So if you want to know how many, so the column represents the sample. So if you want to know how many seconds of data you have, you can take this 121,893 and divide by 500 So that'll give you, roughly the number of seconds that you have of data, and this is actually quite a few seconds of data here. I think we have a couple minutes. So that is how the data are structured. Now, if you're going to do things like make calculations on this data, and you're going to do it within MATLAB, like let's say just for kicks that you wanted to average the value on each channel or average the RMS on each channel, then if you just do an average on class data, it's going to average over the channels per second. So before you do a lot of calculations on the data, it's very important to understand when MATLAB does calculations, it does it by column. So if you want to know, for example, the time average RMS value in channel 1, 2, 3, and so on, then you need to transpose these data so that you're actually averaging what you think you're really averaging. And that's going to be very important because, as you can see, there are some rows, some channels that have relatively larger values, like we have, values in the range of 11 to 20 here. Whereas if you look down here, you're much smaller in your overall amplitude of values. So it is important that before you begin to do any calculations, including filtering, anything you do, that this data set be transposed so that your time number is the column, or so your time number corresponds to rows and the channel number corresponds to columns. So what I'm going to want you to do with this data set are several things. If you remember, this is our unfiltered data, and that's what you have. I have not filtered these data at all. So what we're going to look at, first of all, is we're going to look at, without any filtering, we're just going to look at some power spectral data. And so part of what I want you to do is to come in, and if you look here, let me go all the way back and look at the very beginning. If you look here at the very beginning, you see there's kind of some noise at the beginning. And then we also identified that right here, kind of between 8 and 9 seconds, you have this artifactual component. And then if you continue on, you see it again between 15 and 16. So hopefully you're taking some notes and you're writing this down, that something's going on between 8 and 9, between 15 and 16, between 27 and 29, and so on. So the first thing that I'm going to want you to do with this data is to pick some relatively clear stretches of the data. So for example here, in this region, let me see if I can't view more of the channels here by changing the scale. In this region here, from say 37 to 42 seconds, you're relatively flat. You don't have a lot of those artifactual looking things. There are a few. Here's some noise and so on. Whereas if we come back and we look, I think it was like 28, 29. Yeah, if we come back and we look at this range from 25 to 30 seconds, you can see there's a lot of stuff that's going on here. So the first thing I'm going to want you to do is just to take this data set, load it into MATLAB, and then using MATLAB, find the power spectrum of 2 or 3 different 5-second regions of data, and we're going to assess how stationary is this data set. We already know it's not stationary because we're looking at it, but it would be interesting to know if that actually shows up on the Fourier spectrum. So I'm going to want you to take, we've paged through this and we've found some regions. 25 to 30 seconds is noisy. 30 to 35 does not have that artifact. Let's see if I can find another one. 50 to 55 is also clean, relatively. Looking for some of that crazy. Okay, and this is a different characteristic of noise. You can see we've got something going on here. This is probably somebody clenching their teeth. 80 to 85, we have kind of a different characteristic. So this 80 to 85 range is interesting. The ranges that do not have noise are interesting, and then the ranges that have the artifacts are interesting. So what I want you to do is I want you to pull 3 different 5-second samples. One like what we illustrated, one that's clean like this, one that is what we observed back around 28 seconds, and my computer's frozen, so it doesn't want to do anything. Yeah, one that probably should run from 25 to 30, and then the other one up around that 80 to 85 range where we observe that high frequency noise. That will give you 3 different signatures, and what we want to know is, do these things that we observe that clearly are some kind of either external noise or body artifact, how much, if any, do they influence the frequency spectral characteristics? So you're going to take a 5-second interval at 3 different locations. You're going to need to basically figure out, so 80 to 85 seconds, if I multiply that by 500 samples per second, that'll roughly tell me what sample range I'm looking at, or that'll tell me what sample range I'm looking at. You want to be sure once you select that and create a sub file that you plot that and make sure you're looking at what you actually think you're supposed to be looking at. You don't want you doing this blind. I want to see time domain plots of the data for your 3 different segments that you choose. And so once again, one should contain some aspect of this kind of higher frequency noise that's fairly localized, should be localized roughly in the middle. The other one should contain something like what we observed back between 25 and 30 seconds, kind of like this. And then the third one should be in a region, say like the 35 to 40 seconds, where you're relatively flat and things look relatively clean. So I want to compare the time domain plots of those as well as spectral analysis plots of those. Now, you have 65 channels, so clearly I don't want you to make 65 plots of power spectrum. So when you're deciding what you want to display, so part of what this class is about is teaching you, when you're working with data, what is it you're actually trying to display. You're trying to display, things that are hidden in the signal that may or may not be obvious to the observer. So when looking at the spectrum, I might calculate it for all 65 channels, but then when I'm presenting plots, what I might do is I might select some, so you can see that channel 2 here appears to have quite a bit of stuff going on, as to channel 55. And then if you go back to that plot of the head, wouldn't it be useful when we're doing our analysis to just sort of come in here and look and see, sorry about that, to come in here and look and see, maybe I want to pick one from this region. There's channel 5. It's kind of in the front of the brain. And then maybe I want to look at one back here in the back of the brain and one near the side of the brain. So I might suggest picking 5 or 6 specific channels. Particularly, you will kind of want to coordinate looking at this figure and then looking here at which channels appear to have a lot of a lot of this displacement. And of course you'll be looking at this plot in MATLAB, so your channel spacing will be a lot more easy to see. It won't look like this. You'll be able to view your plot much more easily. So once you select those, that's basically, you're just down selecting the data to look at some sample channels. It'd be great if different groups within the class looked at different channel regions, and maybe I'll even go in and assign different groups different channel regions to explore, and then that way you're not plotting for 64, and then we'll put this together as a whole class and look across the whole brain to see basically how do these artifacts affect the Fourier spectrum. Now, from a point of view of just the physiology of the problem and what people are trying to see, what's going on at different frequency ranges tells you about something about the functionality of the brain. So if you have, for example, a seizure, seizure activity often tends to occur at a specific frequency and it tends to be very normal. I mean, very, very sinusoidal. So if you're having a seizure, that would be a clear shift in a frequency spectral pattern. Well, sometimes if you just have these artifacts show up, they look like things they're not. And so what we want to know is, if you're going through looking at frequency spectral data, can you actually see the difference that these kinds of things make? And would it lead to some kind of false interpretation when in fact all you're really seeing probably is noise? So we're looking for, and then you want to compare the three spectrums of the three different sort of snapshots that you've chosen because we're looking for how stationary is the signal. Then finally, I want you to just take the whole data record without any filtering, without any down selecting for the same channels that you've selected for your initial analysis. I want you to take the whole record and I want you to just do a power spectrum of just the whole thing. And then we'll compare to see if, in fact, these kinds of effects do average out over time. Um, is the spectrum where the data is relatively flat, is that similar to the original, to the spectrum of the entire record, or is it different? So we're going to do that. I'm going to also ask you, do not throw away your data or change your data set because we're going to do some more stuff to it later. So we're going to do this first. And then as we get into chapter 4, where we talk about filtering, we're going to design some filters and look in some different ranges and see, first of all, if we just bandpass filter this, does that clean up some of the problems? And then what happens is we start to look in different relevant ranges. So we're going to use this data set throughout the semester. It's a messy data set. I chose it intentionally for that reason. We're going to use it to apply some different techniques on it. I will probably reshuffle and reassign groups for this project because it will sort of go across the semester. I'm asking for some feedback on that, but basically in this project, you'll work in a group and you'll work with a specified group of channels, and then we'll figure out kind of how to go from there. All right, thank you.